All right, so we made a hard break. We want to we're done with the addition reactions of alkenes. The next conversation starts the addition reactions of alkynes. So instead of having double bonds, we're going to have triple bonds. But at the end of the day, we're going to do essentially all the same reactions that we just learned. And essentially, they're going to have all the same results. There's going to be some caveats in that idea, and we'll have to address those caveats as we come to them. But if you really understand and know the reactions, the addition reactions to alkenes, then you have a really good understanding of what the addition reactions to alkynes will produce. And so, again, it really is a very related subject. And so we're going to do addition of HBr. We're going to do the addition of Br2. We're going to do oxidative cleavage. We're going to do Markovnikov and anti-Markovnikov hydrations. It's just that sometimes those things lead to slightly different but very closely related products. The only new reaction that we're going to do involves using an alkyne as a nucleophile to actually form carbon-carbon bonds. So far, we haven't actually changed the carbon skeleton at all. At the very end of this discussion about addition reactions of alkynes, we will learn a method to change the number of carbons on a carbon skeleton. And that really does provide you with some advanced synthetic skills. And so again, a huge goal for you is to master synthesis. If you're one of the things about mastering synthesis is being able to change the number of carbons from a reactant to a product. But let's save all the conversation for reactions until another day. And what we'll do today is essentially only introduce the last bit of nomenclature for organic chemistry. I guess we do talk about alcohols, so let me kind of back off on that. But you were not going to be surprised about alcohols. You're probably not going to be surprised about alkynes, but there is a little bit of discussion about alkynes and the nomenclature of alkynes. So let's kind of get going on that. And so we'll do a couple of naming examples, and then we'll cut it off for the day, and then we'll see what's up. So this will be a pretty short video in that regard. Okay. So we learned how to name this thing, 5 carbons, all single bonds. That was fairly straightforward, pentane. We added a little bit more complication to it by adding a double bond, which means we could have added a double bond there, or we could have added a double bond there, or the double bond could have looked like this. Oops, the last one is too many. And so the question is what are all of these things names? Well, one of them was 1-pentene, one of them was trans-2-pentene, and the other one was cis-2-pentene. And so adding double bonds certainly complicated our nomenclature, especially when we had to think about something like this. Well, that's 2-bromo-2-pentene, but is it the E version or the Z version, because we can't really think about cis and trans anymore. We're going to need some nomenclature for alkynes as well, and alkynes involves triple bonds. So I'm sure it's no surprise that if we have the simplest possible triple bond of 2 carbons, then we're going to stick together our original nomenclature and the prefixes for the number of carbons, eth, and add the suffix -ine. So this is an example of eth-ine. It's the simplest possible double or triple bond. But as before, we can have things that are more complicated. And I want to stop a beat and I want to just say, when I show triple bonds attached to molecules, I need to show them in a linear fashion. I have seen this so many times, and it makes me cringe. And the reason it makes me cringe is that the geometry, the bond angles around any triple bond, if it's sp hybridized, should be 180 degrees. And that certainly is not a 180-degree bond angle. So make sure that you're correctly showing the geometry of that triple bond. So how many carbons are involved in this chain? 1, 2, 3, 4, 5, 6 carbons. So this is certainly hexyne. But which hexyne is it? Because remember, the triple bond can be in several different locations. Well, we're going to number the carbon chain in a similar fashion than we did with double bonds. We're going to number the chain in the way that gets us to the triple bond the fastest. And so that means we have to number this way: 1, 2, 3, 4, 5, 6. So this is hex 1 yne, or also as acceptable 1 hexyne. Okay, so we don't really get into anything incredibly new. We can add some substituents. Let me say, well, what's the name of this thing? Let's actually make it look good, because of course those are stereo centers. So we can still number it in the same sort, take the same considerations. We're going to count the number of carbons: 1, 2, 3, 4, 5, 6, 7 carbons. We want to number in the direction that gets us to the triple bond the fastest. So this is a heptyne. Which kind of heptyne is it? Well, it's a hept2-yne. What do we have attached to the heptyne? We have a 4-methyl. We have a 5-methyl. And what is the stereochemistry of these guys? I've got a hydrogen here. I've got a hydrogen there. And so let's think about it. It looks like it's going to be 3. Let me back up and use a different color. This would be priority group number 3. This would be priority group number 2. This would be priority group number 1 for this one. So that looks like an R. Yep. Way to go, Carrot One. Looks like an R. What about this other one? Let's use a different color for that one. So it looks like this one will be priority group number 4. What about this carbon versus this carbon? How do we deal with the priorities there? Well, we're going to treat triple bonds the same way we treated double bonds. When we draw a list, we want to write all of the 3 atoms that carbon or that atom is attached to. Well, the purple carbon on the right is attached to a carbon, and a hydrogen. But I'm going to count each bond in the triple bond and say that carbon is attached to 3 other carbons, even though in reality it's only attached to 1, but we're going to count each bond in that triple bond as being connected to the atom it's connected to. And so that means that this is a higher priority group. So 1 is this direction and 2 is this direction. So this one is, where's 3? I'm sorry. Let me back up just a second, because the group that is 4 is the hydrogen. It's pointing away from us. The methyl group is group number 3. I get 1, 2, 3. That looks like an S to me. So if I were to put everything together, it looks like I have 4s5r 4,5 dimethyl hept 2 ine. So there's not much new other than we're adding a triple bond. The only other situation comes in is when, what do we do when we have both a double bond and a triple bond? Well, I don't know if you remember us talking about this, but at the end of the day, a double bond is, ooh, look what I did over here. Ooh, somebody's over there making fun of me, hopefully. At the end of the day, a double bond is higher priority than a triple bond. So the only thing when we have, this is an ene is the type of molecule this is. It has a double bond and a triple bond. The only thing is that we have to number through both groups. Even if this R group is longer, we need to number through the higher priority groups. And while the double bond is higher priority than the triple bond is higher priority than the alkane. And so what we want to get through is then numbering, but since the double bond is higher priority, that means it's going to get the lower value. So we start there. 1, 2, 3, 4, 5, 6, 7, 8. So this is an oct 2 ene 6 ine. That's what this particular type of molecule is. What kind of groups does it have? Well, it looks like it has a 2-methyl and it has a 3-butyl. So putting it all together, this is 3-butyl 2-methyl oct 2 ene 6 ine. Fairly straightforward, I imagine. There is one other level of complication that we can add to it. And I don't actually remember if we did this for double bonds or not. So let's go ahead and take a look at what that might look like. But what if I have something like this? We've got more than one double bond and more than one triple bond. And I've got some stereochemistry to sort out in several different locations. So let's do this as our last example and then we'll be done. What we do when we have more than one group is we say that it would be a diene or a diene or a triene or a triine and so forth. And so what we're looking at here is we've got a diene and we've got a diene. So it will be a diene diene, and we'll have to do the locations for that. Now let's do the numbering. We want to number in the direction that gets us to the double bond the fastest, because the double bond is the highest priority. We want to number through both the double bonds and the triple bonds. And so that gives us the chain. And so if I go here, 1, 2, 3, I get the double bond at the 4th position. But if I go here, I get it at the 3rd position. So it would be 1, 2, 3. Remember, I'm still looking for the longest chain. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And actually, I don't even know what 14 is. I know what 12 is, but I don't know what 14 is. I'm going to, quick like a bunny, look it up. It's tetradecane. Tetra dec. So it'll be a tetra dec diene diene. So let's deal with that. And we'll deal with that in a second. So where are the different things? So it's a, it looks like it's a di, or it's a diene, and the enes are in the 3 and 6 position. It's a diene, and the ines are in the 8 and 12 position. I've got a methyl group in 11 position. It looks like it is a 3. This is third priority. I think this is priority number 1. This is priority number 2. So it's 1, 2, 3. That looks like an R to me.
Professor, wouldn't there be a methyl at number 3 as well?
Yep, I'm going to get to that in just a second here. So the other question, so let's go ahead and write that down. 3 methyl. Thank you. Another question was asked, if you want to get to the double bond the fastest, why wouldn't you start from the bottom carbon? And I think that means you're thinking about this carbon. And so if you want to, yep. And so why wouldn't you do that? Because then that wouldn't be the longest chain. Because you do want to get to the double bond the fastest, but you want the, we're going to get to that one just a second. You do want to have the longest chain as well. And so we're also having pointed out that there's a 4-ethyl group. But I do have some stereochemistry. So what did we say about this? Was this methyl group was R? What else do we have to think about? What's the stereochemistry of the double bonds? Are they E or Z? Well, the first double bond, I don't have to, it doesn't matter because it's we would say that it's cis. So we could just say cis there, or let's go ahead and call it E and Z. So this one is low priority. This one is high priority. This one is high priority. This one is low. So this is opposite. This one is E. What about this other double bond? This one is high priority. This one is low priority. This is low priority. This is high. So this double bond is Z. So we've got 3E, 6Z. Here's our stereochemistry. And let's see, do we have anything else going on here? Yep, we've got a group at the 7th position. What is that? That's a propyl group. All right, so let's take this real quick. I'm just going to shrink it just a little bit. And so let's try to put it all together. I've got 3E, 6Z, 11R. And then what comes first? Ethyl or methyl or propyl? 4-ethyl. Then I've got 3,11-dimethyl. 7-propyl. Now I think so we've got that, we've got that, we've got that, we've got that. So we need to do the tetra. Okay, so we've got tetra dec 3,6 diene 812 diene. Fun times. 7-propyl. Yep. Fun times. So I'm going to stop the video right there. That's it for the